Okay. Hi, everybody. The talk is, it's not important. It's not important. This is also not important. You can hear me all, right?
Yeah.
I just wanted to make a fix for one of the mistakes that the previous presenter made. Not the C++ mistake, but I'm not a cute guy anymore. In essence, I do work for KDAV, which is a company that contracts blah, blah, blah. And we do work with a lot of Qt, but lately I'm pure C++, thank God. You can cut this from the recording, right? And apart from that, I'm also an significantly more inactive member of C++ committee than Alex is. And from his talk, you kind of see the reasoning why many people are inactive in C++ committee. Essentially, my last in-person meeting was the time when they discussed one of the previous versions of pattern matching, and it was fun. I'm not going to say anything else because I'm recorded. So, for people who don't know me, this is the quote that I start all my talks with. It's not really a quote by Phil Wadler, but I did hear him say it, so I'm attributing the quote to him. Make your code readable, pretend the next person who looks at your code is a psychopath, and they know where you live. So this is something to live by. And obviously, I like to put a picture of Phil Wadler in his Lambda Man dress up. So, as a small introduction, a long time ago I was young. And I started, let's say, writing some code quite early on. So when I enrolled at the university, I thought that obviously I knew it all. And for the first 2 years, I just coasted and didn't listen to anything that I was told because the exams were trivial and you don't really need to learn anything. The problem that I skipped back then and that most of my students afterwards tend to skip is a small chapter in our book that talks about idioms in a programming language. And idioms, why do we need to know what an idiom is? We can understand the code that we wrote. Everybody who knows the language will understand whatever we write in that language. But anyhow, the idioms are really important for several reasons. Usually, people talk about it's easy to write, because if you have something memorized in your fingertips, it will just flow out of your hands. It's easy to understand for other people. They don't need to invest time to understand your code because it's idiomatic, so it does what that idiom tells you to. And obviously, since it's easier to understand, it's also easier to debug. But another thing which is really important, especially in the recent years, is that idioms are safe. Nobody will ever design an idiom in a programming language which will crash the space station or kill a bunch of people. All the idioms are designed to be safe code apart from something else. In this situation, so the ugliest programming language in the world, C, because that was the book where I should have learned idioms in. We have an idiomatic for loop, and obviously we all know that this is an idiomatic for loop. What is the guarantee of this? There are no bugs in this for loop if you just access persons of I. You cannot ever have outside of bounds read not with a lower I or a greater I. Because you have an idiom that says, if I have an array of n elements, I'm perfectly safe to iterate over it with this for loop. And this is mathematically provable that this is safe code, if the prerequisites hold. So if you have a code like this, and at some point you have, I don't know, some sanitizer complain inside of this for loop, you know that the bug isn't there. The bug is somewhere outside. So you have crashed the prerequisites. The idiom itself is perfectly fine. So if you write a lot of code in idiomatic style, then you will be able to easier to pinpoint where the actual issues are by just skipping those parts and focusing on the non-idiomatic parts of the code. Now, if we move to C++, we have now the UZ for std size t literals. And if we encompass, like std vector does, the size into the object itself, then you don't even need to care about the prerequisites anymore. The prerequisites are automatically guaranteed by the std vector. So this will be a perfectly valid code if you use the idiomatic parts of it. So if you're in a for loop that is meant to traverse the elements of a vector, the idiomatic way is to just look at the current element. Using the vector itself inside of the for loop is non-idiomatic. It is most likely safe if it's read-only, but as soon as it's not read-only, you can get crashes. And the same thing about index. If you do it, if you just use const access, so non-mutated, it's perfectly valid and provable safe code. And obviously, in modern, contemporary C++, we also have something that is even better, so we don't even have the opportunity to screw up the index while iterating over a collection. And Sergey is laughing because I said modern C++, even if I really hate that conjecture. So obviously, now we are all grown up. We don't use for loops anymore. Now we switched everything to algorithms in the standard library, as we should. And the idiomatic safe way to use std transform is if we have an input collection, the first two arguments need to be iterators from the same thing, so words something dot begin, words dot end, and we have a back inserter to some result. And again, this is perfectly safe code, easily to prove. The idiom here is that obviously the first two arguments need to have the same collection before the dot. Now, what happens if we say std vector result and then std transform? Who is going to complain about this code if you get it in code review? Okay, can we shout why? Or you can use make.
It can be better.
It can be better, how?
By reserve.
Of course. So we immediately know that we are going to take n elements inside of the vector. So this idiom tells us that we should, whenever we have an empty vector, and when we have transform and back inserter into that vector, we should call reserve beforehand. And again, this is not about safety, but it still is a safe idiom. This is now idiom that is mostly focused on performance, but not by sacrificing the safety. But is this the most performant way?
No, you don't need the back inserter for this. You can now just use begin.
We can use begin and we can use resize. Now, this is not safe code if you don't see the first two lines. You're calling std transform into a collection which might not have enough space for all the elements. So here we have a really dangerous and problematic operation in general, writing into something that we might not actually have. But inside of this idiom, this is again perfectly safe code, and again, it's mathematically provable that it's a safe code. Okay? And this will be most likely, in many cases, faster than the previous one because we are not going to have any branching inside. Are we at the end of the collection? So we can just write. So that's the reason why idioms are really important. If we are able to write as much of our code in an idiomatic way, then we'll not have the need for some, let's say, pretend safe languages out there. And if somebody wants me to explain this sentence, we can do it afterwards. So let's see one stupid idiom that you've seen in Alex's talk as well, just hidden a little bit. Just imagine we have a scope and we have a variable of a certain type, and we want to have the same variable in the rest of the scope under a different type. Now everybody's confused because obviously C++ doesn't allow us to have anything like this. But we kind of have some trickery to simulate parts of it. So So if we need to calculate something, and after calculation it should be const, then we, sorry, then we all know what we should do. Imagine the following code. So we have a person, just like in Alex's presentation, just with lowercase p, and it's Martha Jones, but the constructor doesn't accept everything that we want to do with said person. By default, we should all define everything as const. And as soon as we have something like, we just need some tinkering, some slight changes to the value, we remove the const and we remove the promise that our type is no longer to be used after these two lines. And again, we are opening ourselves to having bugs a little bit later on in the function because we have switched one of the compiler's checks. And we all know what should we do. My throat is... An idiom that exists in all the languages that support lambdas, under different names. In C++, it's often referred to as immediately invoked lambda expression. So you create a scope where a certain variable is going to be non-const. You put that scope inside of a lambda. Lambda returns the value, and outside of the lambda, it's going to be a const object. Thankfully, the compiler will be smart enough with return value optimization, etc. So this will not really be a separate person. The person inside of the lambda and the person in the outer scope will be the same person, the same object, just the outer one will have one guarantee more, it will be const object, which is cool. So we have lifetime, no lifetime issues here. We are returning objects, so no references, no pointers, nothing else. So this is perfectly safe in that regard. We have const guarantees, but we do have some limitations. The first limitation is obviously that this is not the same scope as I tried to announce that we are going to implement something like that in C++. And because it's not the same scope, those are different scopes, then you cannot have several variables intermingled and all depend on each other. When you want to define new variables, they just need to use whatever is defined above. You cannot mutate something, mutate, and build the result in the end. But even if it's a limitation, it's a good limitation. It provides you with safety. You should never have the code that cannot be rewritten like this, because that means that you have completely screwed up the dependencies between your variables inside of a single scope. So this will force you to, let's say, design the dependencies in a tree-like structure instead of an arbitrary graph. If you like the immediately invoked lambdas, but you want something more powerful and you want to chunk your function even into more scopes and convert the different types into not only from int to const int, but from int to string, from string to person, from person to, I don't know, again, int, then you can implement something like and then, which we know from std optional, std expected, or you can call it transform, which we know from obviously STL and the ranges library. Just you can implement it for the normal values. You don't really need to have a container in order for the concept of and then to be applicable to it. And you can just chain several of these and thens, and in the end you get the final value that you tried to calculate. Again, by splitting the big scope into smaller ones, you're again cleaning up all the internal interdependencies between the variables, and you explicitly say this variable depends on this, and that, and nothing else. Now, you can call this and then, you can call this transform, or if you're really creative like people who wrote the Sanders proposal, you can call this let value. And then let the audience figure out what let value means. I never miss an opportunity to take a jab at let value as a function name. So the idiom that we kind of explained is something that we all know and use quite often. And it's something that people often refer to as builder pattern, just a little bit more generic. With a builder pattern, you would create an object that has all the member functions which let you build something in steps. With something like that, you can have normal non-member functions, you can have member functions, you can have whatever you want, and you will still have the builder pattern as you're used to. Any questions with this code? With regards to the safety. Any problems that we usually tend to say, never do this in C++? Well, in the end, we do want to have the person from the person builder, so casting should be fine.
Yeah, that's kind of what I'm unhappy about here is that every function here returns a builder, but the last one returns a person. So when you're trying to extend this with another, and then you need to, you cannot just add another and then you need to fix the previous one.
Depends. Usually in the builder pattern, you end up with .build, which is essentially this. If you want to extend the building steps, then obviously you put and thens beforehand. And if you want to extend post-process the person, then you just go below. So it's kind of like the pattern matching you mentioned in order. The order here is obviously really, really important. The issue that I hoped that you will notice is this one. Returning references from a function. Very, very dangerous. So again, a really dangerous operation in C++. Is it dangerous here? Obviously, that's not going to be the answer. What we get in this function is a reference to an object. And this reference communicates to us, we are never going to use the original value in that object. You can do whatever you want with it. Okay? Then we are doing something with that object, and we are returning the same reference. If we're using this as a builder pattern, this means that the builder object will be the same one, the same instance of the object will be through all of these and thens. We are not creating new objects at any point.
Well, it's not guaranteed that Lambda does that, right?
Sorry?
It's not guaranteed that Lambda actually does that.
In what sense?
You can create the person builder inside of the Lambda and return the new reference.
Of course. But that's why I set this up in a builder style thing. We'll explain later the full idiom for lambdas like this. So you get an object, you do something with it, you return the same object, the reference to the same object, pass it on, pass it on, pass it on. So as far first as performance goes, it's really important for C++ developers. It will compile out to essentially calling several setters on the same object as if there were no lambdas in the play. So all the returns, all the lambda calls will be completely optimized out, which is quite cool. And on the other hand, this doesn't look like we are doing any mutable state. Because from, let's say, mathematics point, we are not. Somebody has a value. And that person promised never to use that value, so they will never again check the value inside of that value. And then we can do whatever we want with it. It's not mutation because it's not observable. So we are in immutable language even if C++ is not. And then C++ is smart enough to actually convert that to normal imperative code that we all love and dread. Now, there are a few things with this idiom that you need to follow. The first one, when you store something inside of the variable, you can never use a reference there. It needs to be a value. So you can pass this reference around as many lambdas as you want. Once that you have done the final processing, you need to bind it to a proper value. You cannot use const.ref. Because at that point, you might create a reference to something that is destroyed when the compiler sees this semicolon. So the first rule in the idiom is do whatever with references here. So pass by reference and catch by value. And the second rule of the idiom is you need to return the same object that you got. So whatever you get from somebody, you just pass on. You get something, pass on. You cannot create a new object and pass that one on. Obviously, you can do the usual switcheroo. You get one object, completely changed it, and it's a completely new object, right? But you need to use the same, let's say, memory that you've accepted here. You need to return the same address in the result. Now, one of my pet peeves with C++ is that we do have rules, and then we have the exceptions. So obviously, we need to declare everything as const. If we declare everything as const, then we cannot get into confusion with mutable state, etc., etc. But we cannot declare everything as const. So everything, but not everything. You cannot really have const member variables. You're going to screw up with assignment operators. You're going to screw up, well, that one is a given. You're going to screw up with move semantics. In essence, don't. Then, if you want to return something from a function, then don't declare it as const, because in the case that compiler cannot do the return value optimization, then it cannot move from that value into the result. So again, you're kind of screwing up with the move semantics. And the same thing with variables that you want to give to another function. If you're not going to use a value, obviously you're going to call std_move on it when you give it to somebody else. But if you declare it as const, then again, it's going to be a copy. Can we have move-enabled const in C++? Ask him to write a proposal. And then 10 years after, what we are going to have, still we are not going to have this, but we are going to have some feature that resembles this idea, right? If we are lucky, exactly. Pattern matching. Again, if somebody is interested in the story, we can do it afterwards. So we need to create a wrapper. We can create a wrapper called immutable, and inside of it, we're going to have a member variable that follows the C++ rules of not being const. But then all the API on this immutable will be const. So if you declare something immutable of int x, then essentially you have move semantics, but you cannot change the value. So we are going to have, obviously, the copy constructor. We are going to have the move constructor. And we can debate on whether we should have the assignment operators as well. I would say that, strictly speaking, we probably shouldn't, because if something is immutable, it's immutable. But on the other hand, it's quite useful to have it, so I would probably say default here and provide an explanation which nobody will believe, but it should sound believable, that variables and values are not the same thing. We are promising not to change the value, but this variable can contain several different values throughout the lifetime. Did anybody believe this? It kind of sounds like I'm talking something real smart or something, but obviously nobody's saying would believe me. But if you try to design your software in that way to differentiate between variables and values, you can kind of get with a lot of cool stuff. And obviously, all the getting functions need to be const. Alex.
I think a good illustration here would be that you can actually start from scratch, but you cannot put your dirty fingers into the object. That's the kind of the point.
Yeah.
Yeah, but you can start from scratch, and it's a completely new value, even though like it's the same variable.
Exactly. Even so, I didn't want to mention any other language in the talk, but all the languages that don't allow you to mutate stuff still allow you to reuse the variable names. So you can say x equals 42 and then x equals 6. But those are different values and different variables, even if they have the same name. So I'm pretending to do the same thing here. For these things, just never return a reference to t, never return a pointer to t, just return the const t. And if you want to give out the object to somebody, so if you have the refref qualified operator that converts to trefref, then you can just std move the value on to the next object. And we've followed all the rules that C++ forces us to have and created something a little bit above that fits our needs a little bit better. So if you want to create a function called getPerson, we can just say immutable person t result something something and then return that result. Inside of the function, result is as good as const, but it's move enabled, it's everything enabled, so you have no performance penalties. And since I've mentioned immutable, I need to mention lazy as well. If you have immutable values and it's trivial to write a wrapper called immutable, it should be also fairly easy to write a wrapper called lazy. So if we have several branches in our code, so several different code paths, and in some of those we use this person, in some of those we don't, some of these we use the person several times, then we can just create a lazy value and explain to the compiler how that value is going to be evaluated once it's needed. And when it's needed, then this lambda will actually be invoked and passed to the function. If you try to use the object several times, it will again be calculated all in once. And the calculated value will be reused, reused, and reused. So it's different than just creating a plain old lambda. The implementation is boring. Boring, okay. In essence, copy-paste the mutable type and add a mutex inside, and you'll be mostly fine. Now we have extended the C++ language. We can write, instead of saying auto person, we can just say lazy person, which is really cool. Instead of having to write const auto something, we can just write immutable. So there was a proposal, I have no idea, maybe several times, that const auto is just extra characters. You should be able just to write const x equals 42. And even if C++ doesn't allow us to do so, just write the wrapper and you will even get a nicer syntax than C++ const has. So one of the really important points here. It is fine to implement things that go against the language if you have the reasoning to do so. In essence, that's what standard library does. And I've heard several times in the committee, oh, we are not going to do that. That's not in the style of C++. Who cares? Unique pointer is not in the style of C++. It doesn't leak memory. Right? So the point of the standard library is a lot of times to go really against the language. The language doesn't want to fix something, okay, we are going to do it in the library. std invoke anybody. Which language does need std invoke? C++, because we didn't want to add it in the core language. Okay, fair enough. Okay, now you have it in the standard. Just not where you wanted it. So it's perfectly fine to write small wrappers even if you're going to use them twice in your code base. If they improve that part of the code, improve the safety or anything else, please go against the language. Now, again, class person, it's like two of us synced at some point, which we didn't. And obviously, my person also has a name and a surname. And the slides, I sent them before him, so it's not like I was typing here while he was talking. So one of the idioms that all of these things, if you haven't noticed, are some things that annoy the hell out of me while doing code reviews. Now, I'm growing old and I'm going grumpy, so everything annoys me. And this is one of the, I guess, the main ones that I'm really, really, really trying to tear my hair off every time that I see somebody. We're going to talk about the operator, the assignment operator, for a little while. And one of the oldest C++ idioms in existence that nobody uses, even if they know about it. So just imagine we have Martha Jones here, and Martha Jones transformed into John Smith. For people who are not introduced to Doctor Who, the names are from that TV show from a long, long time ago. So what we want to do here is to assign new names, a new name and new surname to an existing object. The issue here obviously is what if there is an exception. Both of these assignment operators can throw an exception, right? If the first one throws, we are going to have this unupdated, maybe not initialized anymore, or initialized to some garbage, and we will have surname, which is still the old surname. If the first one passes and the second one just throws, what can happen? We have half-updated object. Now, this is not an issue with C++, this is an issue with any language that supports exceptions. The problem is that as soon as you get an error, this is not undefined behavior, this is everything perfectly defined, but you get your program in the state which is undefined behavior for your program. As soon as you're in a state that is not covered by your program logic, and this is unexpected state, so it's not going to be covered by your program logic, you are in a huge, huge area where hackers love to work in. So as soon as you don't have some code that covers all the possible states of your program, it will be exploitable at some point. And this is one of the reasons why I think that no language can fix all the issues, even if they fix some of the undefined behaviors of C++. Now, what we can do is, obviously, swaps never throw, even if variant thinks that they can throw. So move operations, if you ever wrote the move operations that operation that throws, then just rewrite it. Swap needs a guarantee that it's no except, and properly no except, not just std terminate no except. You create a new person, you give that person a new name, new surname. If all of that passes and you do the swap, then the old object is completely updated to John Smith. If this throws, we exit from the function, the object is not, it's rolled back essentially, so it's not updated at any point. If the second one throws again, we exit the function before calling swap, which means that the original object is unchanged. So you have something quite important in database systems that we all ignore when developing C++. So transactions. For the assignment operator, you just create a temporary copy of the right-hand side of the assignment. If that passes, so no exceptions were thrown, then swap. If an exception was thrown, then just exit and you'll be fine. So this is something that is really, really old, and it's called copy and swap idiom. And again, I guess 1% of all my code reviews had copy and swap implemented. Everybody else implemented their own copy constructors, their own copy assignments, move assignments, and all had bugs. If you use an idiom, it cannot have bugs, and it will be safe. The same for move, although, let's say, strictly speaking, this is not really necessary because we promise that move operations don't throw. Now, an additional small idiom. If you want to use copy and swap is generally a useful function to have, you can just use std tie to implement a trivial, easily implement the swap function, you can just tie all the member variables from the left object, all the member variables from the right object, and the std tie will generate a tuple of references, and tuple has already swap implemented on it. So again, it's even really easy to implement.
There's one thing more to mention with the copy and swap. You don't need to test for self-assignment. It automatically works correctly.
True. Obviously, okay, there are a few more things to mention, but I'm going to skip them because they are bad sides of copy and swap idiom. In essence, the performance is worse than if you don't do it, but I always put safety in front of the performance. And one of the crucial cases where the performance will hurt is exactly this. If you don't check for the self-assignment, then you're going to create a copy of yourself and then swap with yourself, which is kind of useless. But how often do we write A equals A equals A equals A? Seriously?
Also, we can generate it as soon as we have reflection, right?
You mean this? As I said, as if he's synced. When I saw that he's going to talk about
One question about the swap you just showed. Does it work if any of the member variables have an overloaded swap, which is not std swap? Does this work as well?
Should be. Never checked, but it had never problems, so I would assume so. In essence, most of the time when you implement swap, you use using std swap and then just call swap, so it's either ADL or it is std swap. So I'm assuming that std tuple uses the same trick. Okay, so if you live in the future, you can combine reflection with this explicit object parameter this, and create something that we'll call a policy to give a tribute to Andre. And if you define something like this, and obviously the assignment operators, whenever you want to turn on copy and swap for your object, you don't even need to implement anything, just inherit from this structure. Now the trick here is, usually these things are implemented with the recurrent, curiously recurring templates parameter, CRTP, which is tedious and ugly, and this is where this comes into play. So when you inherit from this and when you call my object, swap my objects, this will be my object, and in the other, everything else will just work. This will get the non-static data members of your object, and then using std swap, if as a fallback, swap member from self with a member from other. And then implement just the assignment operators as we've seen in the previous slides, and you have a complete policy that you can just easily inherit from. I haven't tested this on Godbolt because I didn't know that there is support for reflection over there. But again, okay. But again, it should work, right? Like everything else in C++. And everything is safe, yada, yada, yada. This is graphical representation of what the swap idiom does, and I really don't want to cover it in more detail than this. The only thing that you need to remember, which again people tend to forget, so that's the 1% of people who did use copy and swap idiom, but whose code didn't work, it does have its own prerequisites. In order to use copy and swap, you cannot have, the first thing that you cannot have is member variables which are references to something. You can have the reference wrapper or you can have a pointer, but you cannot have a reference to something because it will kind of screw up with the copy, which is the same references over there, and then we are swapping the values that the references point to instead of the pointers themselves, so it's a whole hoopla. So just follow this rule and a few more rules. The strange thing is that even if the standard doesn't talk and doesn't use copy and swap idiom, it does mention the rules. Well, it doesn't mention it as the rules for the copy and swap idiom, but it's the same rules. You need to use the same guidelines for when to write copy and swap and how to design your own classes as the rules for automatic implicit assignment operator generation. So the most logical two ones are no reference member variables. If you create a reference member variable, then you're not going to even have the implicit assignment operator. And obviously, if you have a const member variable inside of your object, then assignment cannot exist anyhow. And there are a few more rules that are not really all that important. The idea of swapping is not only in copy and swap idiom, it's literally everywhere. So for people from graphics, you know about double buffering. We are doing something in the background and then just push it as the main object. Essentially the same thing as the copy and swap idiom. Processing collections in separate threads. One of, let's say, non-really C++ related examples, if you have garbage collection with mark and sweep algorithm, you can do something like this. You mark all the objects, then you delete all the ones that are no longer used, which means that all the deletion needs to happen on the main thread, and you're completely blocked whole of your program until the deletion is finished. Obviously, nowadays, no sane garbage collection does this. You can just push it into some collection for deleting later. And again, when you want to actually do the deletion on a separate thread, since those objects are not used by the main program anymore, you can do it in parallel to the main program. What are you going to do? Just like a trash can, you're going to take that trash can, replace it with an empty one, and then destroy the trash can. And whoever uses the trash can didn't even notice that you changed anything. The only thing that needs to be locked here is the swap operation. So the only thing that you need to synchronize is that the person who is producing garbage doesn't see the moment when you're switching the garbage can to an empty one. Okay, now an idiom that I find important, but maybe not as useful. And one of really nice quotes by John Carmack. In essence, the issue is that we have a lot of state in our programs, and obviously we cannot handle all the states. So he's advocating for functional programming in C++, which is quite fun, that you should have everything immutable. As we said, you should declare everything const. But there is something that he didn't really advocate for, but I'm still going to use this quote from him. And those are the invalid states that we mentioned. So apart from being const and not changing the state, when you design your classes, you everybody thinks of a class like a bag to throw the things in. And this is the quote from one of my friends from his talk at Meeting C++. In essence, anytime you need a new value that needs to exist longer than a function, you're going to put it inside of a class. You put it inside of a class, and then you get classes which have a dozen different, completely unrelated variables. In this situation, we have just a few of exactly four. Just imagine we want to connect to a service, and we want to check whether we are loading something. And for example, we want to parse the document object model because obviously we are in a Google building, so we need to implement Chrome. If we define function render, which renders the DOM, then we are going to use contracts, which we don't have, and say, okay, this function can only be called if DOM is if it's a valid pointer, it's not null pointer. Because obviously, if you don't have DOM, then we cannot really draw anything. Then, for execute event loop, JavaScript runs in an event loop. So what it needs that obviously DOM exists. So we have finished the object exists and we have finished loading. So when we load the page, then JavaScript script runs and it's a proper web application. If we have load page, then we have more contracts and saying, okay, the DOM needs to be empty because if it isn't, we have already loaded the page. The state should be not loading. Before we start loading the page, it should not be even connected. So what we've created is essentially one class where each of the functions should work in a specific set of cases. What should have been done? We should have split it into several classes, obviously. But before that, just an example of an invalid state that might happen in the class that we've implemented. Whatever the URL is, obviously the URL as a std string can be an invalid URL, but let's ignore that part. Just imagine we have a connection, we are connected, loading, we are connected, but we are not loading, and the DOM is already loaded. So when we create buckets of member variables, we are creating a lot of different states that our program logic is not going to cover. So a lot of states that are undefined behavior for our program, even if it's defined behavior for C++. So instead, you should use something that separates these things into different classes, into different states. You can implement state machines as in different ways. My favorite, at least for this example, is create different structures. Initial state just needs the URL. The loading state needs the connection, no longer needs the URL because we have established the connection, and it needs the object where we are going to fill in the DOM. And once we are loaded, we don't even need the socket connection anymore. Now, we cannot have any problems, any invalid states in this situation, and the whole page is just going to be std variant of these three states. And to connect to the first item that we've had, we have chunked a big scope into smaller chunks, which are all isolated, and we have clear dependencies between the variables. We have done the same thing here, just let's say in a different area. We have chunked one big class into smaller ones where the member variables are actually connected to each other, and split all the states into three significantly different states of our program. And if you want to process this before we have pattern matching, you can use the overloaded lambdas. I'm assuming that overloaded lambdas were mentioned a million times in the world so that we all know what they are. If they're not, I have 10 minutes. Ask me later. So to-do list. Talk about pattern matching, talk about overloaded lambdas. In other languages. Or a Rust bug. No, sorry, not Rust. I said that I'm not going to mention any names. So the overloaded lambdas, the point of them is instead of using the if const expert that we've seen in the previous talk, we can just create overloaded lambdas with each lambda taking a specific type. So kind of like poor man's pattern matching, just matching on the types. And in all of these lambdas, we're just going to cover a specific use case, specific state of our program. Now, the thing that I wanted to focus here is more this line over there. Just remember that we are visiting a page which is a variant, and we are assigning a new value to that variant inside of the processing function of the overloaded. The same thing if you don't use the overloaded lambdas, but if you use getIf. When we want to switch from one state to another state, we check, is this the correct type? So we have been loading. We finished loading. We are now moving the state to loaded. And again, the same thing happens. We are processing page, and we are changing the page. Any problems here? correct. So we should make it transactional. Now we can say maybe, okay, but this is kind of like constructing, temporary, blah, blah, blah. This should be more operations. So maybe this is safe. But again, this is a good hint. What is happening here? We have our current state. This is loading state. Then we create a reference inside of the handler, so inside of the lambda or via getIf, we get a pointer, to something that is loading state. Okay? We are still in the handler. We are changing the state from loading to loaded. Now we have a completely different type inside of variant. We still have a reference to the old type. Okay? Now, in general, I have never seen this be a problem in real-world code, because you never write these handlers to be really, really, really big. But at some point, somebody will. So what we can do to solve this issue is, again, transactions. If you want to do the double buffering, you can use swap here instead of just the assignment operator. Create a new page, generate the new state, and then if and everything, so all the handlers have executed successfully, then just assign it to page. And a little bit more complete. So we have created an empty state object. We have created a new state called loaded. And once all the references are gone, then we can actually change the type inside of the variant. Now, this might be a little bit annoying to write, but again, this is probably correct. You cannot have any lifetime issues here because we have fixed the only issue that we could have had. Now, if you want to do something a little bit more, okay. Some handlers want to update the state, some handlers don't. Just don't create new page to be page T, but optional page T. And if it's initialized in that situation, and in that situation only, update the original state. So again, quite a cool trick. Sometimes you want to stay in the state that you've been to. If you're loading and you're still loading, there is no reason to switch to another state. You just updated the current state. Otherwise, return the new state and assign it here. And this is code that can be copy-pasted, 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 and we've learned that we shouldn't. So we can just write a new function called visitUpdate, which will be kind of the extension of std visit, which will also perform this updating thing. So std optional, we are going to provide the matcher, so the overloaded lambda. We are going to provide the variant. We are going to create the new variant by visiting the old one and explicitly marking it as const so that we cannot change the original one if we want it to be const. And if we should update the state, then we assign the new value to it. The point of this slide is not that much in the function itself, but in one of the rules for idioms. It's really nice to define a lot of idioms and then write, I don't know, books that cover all those idioms and everybody needs to learn them, etc. But if you can write an idiom into a generic function in C++, obviously you should. You shouldn't force people to learn all of this by heart because they will make mistakes. You should write a wrapper function over the idiom if it's possible. Just like, let's say, ranges transform over std transform. And when you want to call this, then you can just say visit update, std move the old page, and you can even store it into the old page because we already talked about functions that take refrefs and return refrefs. And this will essentially be an in-place update as far as the compile is concerned. I don't have the time, right? Okay, I'm really going really fast through this. This is something that I really don't want to call idiomatic code, because it's an experiment of the worst kind. So the story is like this. Error handling in C++ and any other language. We are making lunch. After making lunch, we are cleaning stuff. But what happens when exception is thrown? When you burnt your lunch? For example, I don't know, you're cooking something and it just starts to burn on the bottom. What do you do in C++ and all other languages? Forget about making lunch, abort, and destroy the kitchen, right? So instead of handling the error, we are kind of running out because there is an error. Instead, it would be much nicer if something started burning, then just take another pot and remove all the non-burned stuff into it and continue making lunch. No need to destroy your home. So when you have a process that could be potentially resumed, the idea is that the continuation, so the callee should explain to the caller how to fix an issue, and then the caller should fix an issue. Again, just imagine you didn't prepare the lunch, but your kid did, and he burnt something, and then you're explaining, okay, how to overcome that issue. So we need two-way communication between components in C++, and fortunately, that is in the standard. We have coroutines, but we need, for coroutines, can communicate kind of with each other. One coroutine calls the other returns something, and it goes on. We just need to create some kind of a protocol between the caller and the callee. So the callee should report errors, for example, through this enum class or whatever error handling mechanism you want to use. And the caller should explain if, I know, this is blinking, so I'm out of time. The other way, the caller should explain how to fix something to the callee. We can create a variant that can be a message, so in one direction or the other. And we can define the result object as expected, which will be a result if everything is fine, so a proper type. And if it's not, it's going to be a pointer to this communication message thingy. And now in the, for example, parser function, so the cook lunch function, anytime that we find something wrong with, for example, parsing, we can initialize this message to be invalid type error, for example. And instead of co-returning the final value, we're just going to co-yield one instance of std unexpected with a pointer to the exact message what happened. Then the caller just needs to say co-await. Co-await will return it a proper value in expected if everything went fine. It will return the pointer to the message if it's not fine. Okay? Then if you want to consider, okay, this is a fixable error, then just advise the coroutine, okay, this line can be skipped. I know that you can't parse it, so just ignore it. And then it can just, again, go back to co-await and call the coroutine again. Then the coroutine continues until it finds another error, reports the error, etc. If all the errors were exhausted and the result was found, then it will just return you the final result, and the caller will see the result and not the error inside of the expected. Now, the thing that is ugly with this approach is obviously the use of a pointer to a member variable inside of the coroutine, but everything should essentially be kind of hidden inside of in some type. The point why I didn't want to clean it up is to use just the standard things. std generator exists as the only use case for coroutines in the standard right now. So this is something that we can use even today. And again, even if it's a pointer, it's safe because the coroutine frame is not going to be destroyed until it's actually finished. Dobra. So, if you're using idioms, it's easier to prove safety. If you use them correctly, then it's easy to prove safety. It's easier to triage bugs because you can ignore the parts of the code which are idiomatic, and easier to prove correctness. Obviously, correctness is never easy to prove, but it will force you to write code in a different way, which will allow mathematicians to prove your code in an easier way than just writing random C++. The downsides, development under heavy chains. If you need to write everything as idioms, you will have a hard time. Almost as if you're rewriting in a completely new language. And obviously it needs more bureaucracy in the design and development stages, and essentially you'll end up rewriting your whole code. The better thing with this is that you can gradually rewrite, and you don't need to rewrite the whole project in a different language. So if you employ test-driven development, also employ idiom-driven development. Every bug that you find in your code, first write an idiom that will fix that bug and never allow it to happen again, and then force people to apply it. Idioms that you can write as generic functions do. If you can write idioms that are checkable by compiler or by an external tool, again, do that. And this is it.
Let's just do one question, and then maybe the rest offline, okay?
You said what we can formulate in idioms we should do, yes. But I still find a book with a lot of idioms in there useful. Can you recommend one, or would you write one?
Yeah, I got that question in Berlin a few months ago. I don't want to write another book at any point in the future. And there are no books that I know that talk about idioms. I think that I invented the idiom-driven development. At least when I Googled the term, I found nothing. So the problem with writing a book on idioms is that if it were to be complete, it would be something like this. So just write your own for whatever you need to write. You don't need to know all the idioms in the world. You just need to know the idioms that work for your domain. I know this is a cop-out, but...
Thank you so much for your talk, Ivan. Thank you for coming.
Thank you for inviting me. And to everybody, obviously.